In the deep night beyond every city and mountain, the universe drifts toward quiet. Galaxies pull away from one another like lanterns carried down separate rivers, their light stretched thinner, their voices lowered to a whisper. Astronomers call it acceleration, but to a poet it feels like a soft, relentless unbraiding. Already, whole galaxies have slipped beyond a horizon that no signal can cross. Their final photons are on the way, but the senders have, in a sense, already gone. Star birth has peaked and is fading. The cosmic microwave afterglow, once furnace bright, has cooled to a chill murmur. Even in the bright rooms of human reason, a suspicion ripens. Perhaps the end is not a sudden curtain, but a long dimming, already underway. The mystery is stark. If space itself is pushing space apart, if some unseen pressure drives the expansion faster with time, then isolation is destiny. Islands of matter will remain, but the great map of everything will fragment into private archipelagos, each forever cut off from the rest. There are worse possibilities whispered in the equations. A fragile vacuum that could fracture without warning, a dark energy that grows without mercy, a rip that unthreads every bond from galaxy to atom. The universe may not only head toward silence, it may be rehearsing it now. This is not doom for the sake of fear. It is an invitation to look with clearer eyes at a cosmos in motion, to ask whether an ending can begin in slow motion, and to learn what the latest instruments, the oldest theories, and the boldest imaginations say about a universe that may already be stepping into its final act. At the beginning of the 20th century, gravity was taught as a whisper between masses, a quiet pull of Newton's design, untroubled by the fabric of space itself. Then a patent clerk turned theorist let geometry breathe. General relativity arrived like dawn on a curved horizon, declaring that matter tells spacetime how to bend, and spacetime tells matter how to move. In the equations, elegance carried a hidden restlessness. Solutions with matter and light did not sit still. They stretched or contracted, as if the cosmos preferred a rhythm over a pose. Yet the culture of astronomy still leaned toward a serene, eternal sky. To preserve that imagined stillness, Albert Einstein placed a counterweight in the mathematics, a uniform energy of emptiness, later called the cosmological constant, so that gravity's tendency to pull could be balanced by a gentle push of space itself. He pictured a poised universe, a bowl held level by an unseen hand, unaware that the bowl's geometry quivered toward motion. Beyond Europe's chalkboards, on a high mountain in California, mirrors gathered ancient starlight. At Mount Wilson Observatory in the late 1920s, a ladder of distance began to take shape from the regular throb of Cepheid variable stars. Their periods, timed like heartbeats, foretold their true brightness, and with that calibration, Edwin Hubble measured the yawning intervals to spiral nebulae that were not clouds within the Milky Way, but other island universes entirely. Their light carried a subtle reddening, a shift that increased with distance. What once seemed a static vault became a moving sea. The farther a galaxy, the faster its retreat, a pattern that could be read as recessional speed equals h0 times distance. The statement was not a mere rule of thumb. It was a clue that the arena itself was expanding, that space was not an empty stage but an elastic medium with a history. In those years, the idea of a beginning, a hot cradle from which everything cooled, lived mostly in argument and inference. The proof would arrive by accident. In 1965, in Holmdel, New Jersey, a faint, persistent hiss haunted a radio horn, a sound no amount of cleaning would silence. Arno Penzias and Robert Wilson had tuned into the afterglow of creation, the cosmic microwave background, radiation stretched by expansion until it was no longer furnace light but a near-uniform bath of microwaves. Its temperature, just a few degrees above absolute zero, whispered of a universe born hot and dense, then thinned and cooled as it grew. The sky was suddenly a fossil, and that fossil fit a story of growth. In its near perfection lay a paradox. Small ripples existed, tiny fluctuations in temperature that would one day become galaxies. But overall, the cosmos was astonishingly smooth and flat on the largest scales, as if an early hand had ironed away curvature and sown the seeds of structure with meticulous care. To explain such poise, theorists in the early 1980s proposed a brief, violent grace: inflation. Alan Guth and soon Andre Lind, and then many others, described a moment when a high-energy field drove space to expand faster than any ordinary process could imagine. In less than the blink of any clock, volumes increased beyond counting. Regions once microscopic lost contact with one another and became the vast domains later seen by telescopes. Quantum jitters, amplified by this runaway growth, froze into the primordial ripples that the microwave background would later reveal as faint temperature variations. Inflation offered an origin for flatness without fine adjustment, a reason for uniformity across far-flung regions, and a factory for the seeds of galaxies. It was a startling claim that the most enormous structures in the universe are the fossilized imprints of quantum fluctuations, stretched across the sky by a burst of early acceleration. The universe, then, expanded from the beginning. That much had hardened into consensus. But how did it expand through the ages of galaxies and stars? As matter thinned with growth, gravity's pull should have slowed the expansion, like a thrown stone rising against Earth's tug. Astronomers set out to weigh this deceleration with exploding stars that could serve as standard candles across great distances. Type 1a supernovae, thermonuclear endings of compact white dwarf stars pushed to a critical mass in binary systems, flare with such dependable peak brightness that, once corrected for the shape of their light curves and the influence of dust, they become admirable mileposts. In the late 1990s, two teams, one led by Saul Perlmutter and another by Brian Schmidt and Adam Rees, gathered a catalog of these far beacons using telescopes in Chile and Hawaii and the eye of the Hubble Space Telescope above the atmosphere. The logic was straightforward. Measure how bright the supernova looks to infer its distance, measure its redshift to learn how much the universe has stretched, and combine the two to trace the expansion history. The result landed with the surprise of a dropped instrument finding a new pitch. The distant explosions appeared dimmer than a decelerating model would predict. The universe was not merely coasting. The expansion was speeding up. Empty space behaved as if it contained a pressure that did not thin away with dilution, a form of energy that remained nearly constant as space grew, and by remaining, pushed growth ever faster. The cosmological constant, once introduced to hold the cosmos still and later dismissed as an embarrassment, returned not as a mistake, but as a candidate for the engine now observed. The picture inverted intuition. Gravity, through the stress, energy of a uniform vacuum, could act repulsively on the largest scales. Skepticism sharpened the analysis. Were the candles truly standard? Could dust be tricking observers, dimming light preferentially with an unusual spectrum? Teams subdivided samples by host galaxy type, corrected for light curve stretch with care, and sought independent verifications that did not rely on exploding stars alone. If acceleration was real, it should imprint itself not only on the distances to cataclysmic beacons, but also on the geometry and growth of structure throughout time. Evidence gathered from the oldest map in the world, the cosmic microwave background. Satellite missions, first the Wilkinson Microwave Anisotropy Probe and later Planck, charted the tiny temperature anisotropies across the full sky with exquisite detail. Their statistics pinned down the universe's spatial curvature as very near zero, measured the density of ordinary matter and dark matter, and revealed the scale of the primordial ripples set by early physics. When those parameters were combined with the distances inferred from supernovae, the joint solution pointed to a cosmos dominated not by matter, but by a smooth component, dark energy, comprising roughly 7 parts in 10 of the total energy budget today. The angular positions of the microwave background's acoustic peaks told of a flat stage. The distances to supernovae told of a stage that was stretching faster with time. Together, they demanded an agent that behaved like a cosmological constant or something close to it. Another ruler, grown in the first 400,000 years, offered a separate check. Before atoms formed, the young universe was a plasma in which sound waves rippled outward, leaving a faint preferred scale in the distribution of matter when the plasma cooled and photons decoupled. Billions of years later, that scale survives as a subtle excess in galaxy separations, a standard ruler known as baryon acoustic oscillations. Redshift surveys that mapped millions of galaxies, sweeping the sky with spectrographs to measure the stretching of their light, found this imprint and used it to trace the expansion at different epochs. The ruler's apparent size, compared across time, matched the story told by supernovae and the microwave background. The universe's growth had passed from a matter-dominated slowing to a dark energy-dominated acceleration. Meanwhile, the very shapes of distant galaxies, slightly stretched by the gravity of intervening mass, gave a measure of how quickly structures clumped under gravity's pull, weak gravitational lensing as a cosmic seismograph. The rate at which clusters of galaxies assembled, the bulk motion of galaxies across space, the way deep voids and thick filaments arranged themselves, all became data streams braided together. Each thread alone allowed alternative doubts. Together, they tightened a net that caught the same fish. By the 2000s and the 2010s, a concordance had emerged, not as dogma, but as a silhouette outlined by overlapping lights. A simple model, cold dark matter plus a cosmological constant, accounted for an astonishing range of observations from the infant universe to the present day. The numbers could be written in the language of density parameters and equations of state, but the translation into story was direct. Matter governs the early choreography, dark energy takes command in the late act. With command comes isolation. As the smooth energy remains nearly constant while space grows, its relative influence increases, and the global expansion gains pace. Regions beyond a certain distance slide irretrievably over a horizon of communication. Their final messages are already en route. Star formation, once a cosmic blaze, dwindles with the thinning of cold gas. The stelliferous era begins to ebb. In that convergence, the nature of the mystery shifts. The question is no longer whether the universe expands, nor whether it began in heat. It is whether the late acceleration signifies an ending already unfolding, a long entropic diminuendo, rather than a mere phase in a cycle. The historical arc, from Einstein's balancing act to Hubble's receding galaxies, from the microwave afterglow to inflation's first breath, and from supernova dimming to the stitched agreement of rulers and maps, delivers a single unsettling inference. The cosmos is not only expanding, it is being pushed towards solitude by something smooth and persistent woven into emptiness itself. The discovery phase, taken as a whole, reads like a time lapse, a static universe rejected, a dynamic one embraced, an origin illuminated, and then a surprise, acceleration forcing a reckoning with destiny. What began as a search for distances ended as a glimpse into the future, where the question of whether the universe is already ending ceases to be melodrama and becomes a logical continuation of the measurements themselves. The result did more than adjust a parameter. It turned the logic of gravity inside out. In the long education of physics, gravity was the art of attraction, a patient pull drawing matter together, braiding gas into stars and stars into galaxies. General relativity allowed a richer grammar. Pressure and energy both curve spacetime, but the emotional picture remained. Gravity binds. Acceleration of the entire cosmos said otherwise. In the field equations, a perfectly smooth energy-filling space exerts pressure so negative that it acts, gravitationally, as a repulsion on the largest scales. The universe was not merely expanding because of ancient inertia. It was being urged to expand faster by something woven into emptiness. That was the shock. The vacuum itself became an actor. Spoken in plain terms, the rule that determines whether expansion slows or quickens depends on a simple ratio: the equation of state parameter, which compares pressure to energy density. When that ratio is less than -1/3, expansion accelerates. For a pure cosmological constant, the ratio equals -1. No chalkboard demonstration could soften the strangeness of this. Pressure, once an intuition of push, could, as part of gravity's bookkeeping, pull on the sign in the equations and drive things apart. The discovery did not violate Einstein's theory. It revealed a less intuitive side of it. Yet to a community that had long treated the vacuum as a stage rather than a force, the implication felt like a rearrangement of common sense. At the same time, a deeper puzzle opened like a trapdoor beneath understanding. Quantum field theory, the framework that so precisely predicts the magnetic moment of the electron and the behavior of particles in colliders, suggests that every field contributes zero-point energy to the vacuum. When those contributions are summed with a naive cutoff, the expected energy density of empty space dwarfs the observed value by a factor of roughly 10 to the power of 120. Even allowing for more sophisticated regularization, the mismatch remains an insult to proportion. Why should the vacuum's energy be so stupendously small and yet not exactly zero? And why, in this cosmic moment, should the density of that smooth energy be comparable to the density of matter, so that acceleration turns on just as sentient beings evolve the tools to notice it? This coincidence problem, why now rather than long before or long after, pressed an existential ache into a technical debate. Acceleration carried another, quieter upheaval. The horizon changed. In a slowing universe, light from ever more distant regions can, in principle, reach an observer given enough time. With acceleration, there exists a cosmic event horizon, a boundary beyond which events are forever sealed off, no matter how long one waits. The light from galaxies crossing that boundary will arrive for a time, then cease entirely. Beyond it, nothing done there can influence anything here. This was not a poetic boundary. It had thermodynamic teeth, a spacetime that approaches a de Sitter state, one dominated by a cosmological constant, behaves as if the horizon possesses a temperature, faint but real. That temperature is equal to h bar times the Hubble expansion rate h divided by 2 pi kb. In other words, even the emptiest future is not perfectly cold. It whispers with a horizon heat, the way a black hole radiates with a temperature at its boundary. Information and entropy follow, like footprints behind the horizon's physics. The observable universe acquires a maximum entropy proportional to the area of that horizon, and the total number of distinct quantum states that can be explored becomes finite. These are not metaphors. They are theorems dressed in the calm of late-time spacetime. With a horizon comes amnesia. Distant structures do not merely fade behind redshift. They move into a realm that no experiment can ever contact. Cosmology becomes more local with time. The growth of structure, once a communal endeavor of clustered galaxies across vast webs, continues only within remnant islands that remain gravitationally bound. The local group, a modest city-state of stars, will endure. Beyond it, the lights go dark one by one as their last photons pass, and nothing more can cross the horizon. The long-term energy economy trends toward impoverishment. As expansion stretches wavelengths, light loses the capacity to do work. Free energy dwindles. Entropy increases with the inevitability of an incoming tide. The age-old vision of heat death, an equilibrium where gradients smooth away and no engines can run, gains a precise trajectory under acceleration. The arrow of time, already defined by entropy, now points toward a particular kind of dusk. The shock also invited darker possibilities. The observation that acceleration can be caused by a smooth component does not compel that component to be constant. If the ratio of pressure to energy density dips below -1, in what theorists call phantom regimes, expansion becomes superaccelerated. Distances race apart so rapidly that a finite time in the future sees all bound structures unbound. Galaxies, star systems, and ultimately atoms would be torn as the expansion's pace overwhelms every force. The countdown to such a big rip can be written, in principle, as a finite number of billions of years, given a measured ratio more negative than -1. Measurements today are consistent with -1 within uncertainties, yet the very possibility of such a fate chilled the imagination. It was not dogma. It was a reminder that the discovery had opened a family of futures, some gentle, some catastrophic, all governed by the behavior of a component that could not be seen directly. Another possibility sits even closer to the bones of particle physics: metastability. The measured mass of the Higgs boson, when combined with the mass of the top quark, places the current vacuum of the Standard Model near a boundary between absolute stability and a local, but not global, minimum of energy. If the vacuum is only metastable, then quantum tunneling permits a transition to a lower energy state. Such a transition would begin in some distant patch as a microscopic bubble and expand at nearly the speed of light. The wall would carry new physics, changing the values of fundamental constants and the structure of forces. Chemistry would fail. Atoms would not survive. Nothing recognizable would remain. There would be no warning because no signal can outrun the front. In that austere sense, an ending could already be underway somewhere unreachable, advancing toward regions that can never learn of it until the instant of arrival. The universe could be both ordinary and doomed in the same breath, not as melodrama, but as a logical consequence of how quantum fields inhabit spacetime. Even setting aside such apocalyptic variants, the acceleration raised philosophical hazards. If a de Sitter horizon contains a finite entropy, then the space of possible macroscopic histories is limited. Over unthinkable timescales, thermal fluctuations could in principle produce rare, low-entropy configurations, Boltzmann fluctuations, that include self-aware observers with false memories. This thought experiment, proposed to clarify the meaning of probability in a finite-state universe, threatened to undercut ordinary scientific inference. If typical observers are thermal accidents, how can reliable knowledge be built? The usual escape routes invoke initial conditions that suppress such outcomes, or dynamics that avoid a true de Sitter end. But the very need to entertain these questions showed how acceleration forced cosmology to rub against the edges of epistemology. The shock was not only theoretical, it altered the practical horizon of measurement. In an accelerating universe, signals emitted beyond a certain distance will never arrive. The cosmic microwave background, already stretched to millimeter wavelengths, continues to redshift. In deep futures, its peak will be carried to such long wavelengths that it passes through plasma in galaxies rather than around it, becoming impossible to detect from inside a bound structure. The Hubble expansion will become unmeasurable locally, because there will be no external galaxies left within view to serve as test particles on which to hang the curve. The universe will remain large and diverse in itself, but for any single island of observers, the cosmos will appear to contract into a private sky. The capacity to reconstruct the full history will erode. That destiny is not speculative poetry. It is the logical consequence of acceleration sustained over time. And yet the most destabilizing feature was how calmly the data agreed. Type 1a supernovae said acceleration. The pattern of hot and cold spots in the cosmic microwave background, interpreted with general relativity and simple early universe physics, invited the same conclusion. The baryon acoustic ruler, measured across different surveys, concurred. Weak lensing, cluster counts, and velocity flows joined the chorus. The model that emerged, cold dark matter plus a cosmological constant, was offensively simple in form and obstinately successful in fit. Its severity angered theorists who had hoped for more structure or a clue that pointed toward new symmetries. Instead, they received a number masquerading as a law, an energy density of the vacuum small enough to let galaxies form, large enough to take over late, and unresponsive to expansion's dilution. The shock, then, was double. The universe accelerates, and it does so in a way that is both theoretically confounding and observationally mundane. There is a final edge to the disturbance which curls back to the central question. If acceleration is real and horizons are closing, then the universe is already, in principle, partitioning itself into disjoint domains. Communication is dying not with a bang but with an asymptote. Heat death is not a theory to be posed at the end of textbooks. It is a trajectory that has begun. Even the most merciful version of the future, no big rip, no vacuum decay, unfurls as a long, cooling twilight. The discovery did not announce a specific doomsday. It announced a policy of the cosmos to expand faster with time. The consequences of that policy play out across eons, but the first moves are visible now in the measured dimness of distant supernovae, the geometry of ancient light, the rhythm of clustering. The universe may be flourishing in the present, but its large-scale fate has tilted. That tilt gives meaning to the next task. Shock is not an endpoint. It is a directive to measure more closely, to test whether the smooth energy is truly constant or only appears so, to watch how structures grow in the shadow of a horizon, and to ask whether the end of everything is a roar, a whisper, or a rule already in force. Shock gives way to discipline. The claim that empty space pushes faster with time is not carried by a single line of evidence, nor by a single style of measurement. It is built the way an arch is built, stone set against stone, each piece supporting and testing the other until the span holds its own weight. What began as dim supernovae becomes a tapestry of distances, angles, growth rates, and fossil ripples, stitched across the sky and across decades of patient observation. The journey returns first to the candles that lit the way. Type 1a supernovae, once treated as near-identical beacons, are now read like nuanced sonatas. Their light curves are stretched and standardized, their colors corrected for dust that can redden without behaving like dust in the Milky Way, their host galaxies cataloged, because the environment of birth imprints on the final blaze. Near-infrared observations reduce the tricks played by dust and improve uniformity. Low redshift samples anchor the latter. Higher redshift samples outline the change in cosmic tempo. Selection effects are hunted Malmquist biases that prefer brighter explosions, survey cadences that miss the faint or the fast. The result is not a single Hubble diagram but a suite of them, pruned and cross-checked, each yielding the same shape. A universe that slows in its youth under matter's grip, and then, as the density of matter thins, bends toward acceleration. The candles have not grown complacent. They are continuously recalibrated with independent yardsticks, so that their message does not stand alone. Those yardsticks reach deep into the earliest light. The cosmic microwave background is not only a glow, it is a score etched with acoustic peaks whose positions and heights fix the proportions of the universe. Satellite maps of temperature anisotropies, refined with polarization and lensing reconstructions, reveal a geometry that is close to flat, and a composition in which ordinary matter is a minority partner. These maps also carry a late-time signature, the integrated Sachs-Wolf effect, in which photons climbing out of evolving gravitational wells gain or lose a whisper of energy as dark energy changes the depth of those wells. By cross-correlating microwave maps with surveys of galaxies, essentially asking whether hot and cold spots line up with overdensities and underdensities, observers extract a faint but consistent signal that the gravitational landscape has evolved in the fashion expected if a smooth energy has come to dominate the dynamics. In this way, the most ancient light speaks about the most recent change. Between the afterglow and the present lies a standard ruler written into the cosmic web, baryon acoustic oscillations. In the first few 100,000 years, sound waves flowed through the hot plasma, coupling matter to radiation. When the plasma cooled and neutral atoms formed, those waves froze in place, leaving a preferred separation imprinted in the distribution of matter. Billions of years later, that scale appears as a slight excess of galaxy pairs separated by roughly 150 megaparsecs in comoving distance. Redshift surveys map this feature across cosmic time, translating it into distances that test how the expansion has unfolded. The strength of the method is its geometric honesty. The ruler's true length is set by early physics pinned down by the microwave background, so its apparent length at different redshifts encodes the history of expansion. Repeated across independent surveys, with different telescopes and strategies, the ruler has told the same story as the candles, but in another dialect. Light does not only measure, it also bends. Weak gravitational lensing, the systematic stretching of distant galaxy shapes by the gravity of all the matter between source and observer, traces the growth of structure. Because the rate at which clumps grow depends on both the amount of matter and the rules of gravity, cosmic shear maps provide a complement to distance measures. They answer a slightly different question, not how fast space stretches, but how eagerly matter gathers under the same laws. Tomographic lensing, sorting galaxies into redshift slices to watch growth through time, adds depth to the picture. The measurements are delicate, intrinsic alignments of galaxies, where neighboring systems point in related directions for reasons unrelated to lensing, must be modeled. The point spread function of each instrument, the tiny optical distortions introduced by atmosphere and mirrors, must be understood at a precision that turns engineering into a kind of poem. Photometric redshifts, estimated from colors rather than spectra, must be calibrated so that galaxies are placed in the correct slices. Despite these hazards, maps from independent projects have converged on consistent measures of the amplitude of matter clustering. When those measures are compared to the predictions of the microwave background carried forward under standard assumptions, a small but persistent tension appears. The late-time universe seems, by a modest amount, less clumpy than the early snapshot would forecast. Whether this is a new hint of physics, a mischief of systematics, or a coincidence in data is not yet settled, but the very existence of such a puzzle serves the deeper investigation well. A theory untroubled by anomalies goes untested. A more audacious test waits with the patience of decades. In a universe whose expansion changes with time, the redshift of a distant object should drift ever so slightly if observed with exquisite stability across many years. This redshift drift, sometimes called the Sandage lobe signal, is conceptually simple and observationally brutal. Quasar spectra, etched with the fine comb of hydrogen absorption in the intergalactic medium, offer the possibility of measuring that tiny change. The precision required is fierce, the timescale is long, but it would be a direct observation of the expansion's acceleration, free of the ladders and rulers that tie together other methods. Such a measurement would be like hearing the universe's heartbeat slow and quicken without needing to infer the rhythm from the motion of a dancer's limbs. While the scaffolding of cosmic expansion is assembled, another reconstruction proceeds in parallel, the archaeology of starlight. By counting stars and measuring their properties in galaxies near and far, by tallying the ultraviolet light from young stellar populations, and the infrared glow from dust that hides star formation from direct view, astronomers have charted the cosmic star formation history. The curve rises from the earliest dawn, swells to a broad peak when the universe was a few billion years old, and then declines to the present day. New facilities that see deeper into the infrared have found abundant bright galaxies in the early epochs, prompting revisions to how quickly the first generations of stars and black holes formed, and how rapidly dust was produced. Interferometers that tune to the cold breath of molecular gas weigh the fuel for future stars, and find it becoming scarcer in ordinary galaxies as time advances. The stelliferous era was never eternal. It is a chapter. Acceleration adds a new layer to that narrative. As space grows faster, the supply lines connecting galaxies weaken, and the chance that even rare gas-rich mergers could restart a fatting metabolism diminishes. The cosmic factory slows not with a crash but with a long exhale. Closer to home, local measures of the Hubble expansion rate have sharpened to a point and then struck flint. Distances to nearby galaxies anchored by Cepheid variables, geometric maser disks, or the tip of the red giant branch provide calibrations for supernovae in the relatively nearby universe. yielding a value of h0 that is higher than the value inferred by taking the microwave background's early universe parameters and evolving them forward under the standard model. The difference is not a quarrel over rounding. It is a persistent gap that has survived methodological cross-examination. Gravitationally lensed quasars whose light paths around a foreground galaxy differ in length supply and independent distance measurement through their time delays, and tend to fall between the two camps, offering nuance rather than finality. Standard sirens, gravitational wave events with electromagnetic counterparts that provide distances without a cosmic ladder, have begun to weigh in, their early results too uncertain to arbitrate but promising a future where they will. The community resists the seduction of tidy answers. It catalogs possibilities, subtle unidentified systematics in one or more methods, new physics in the early universe that alters the sound horizon used by the microwave background, gentle deviations from a perfectly constant dark energy, interactions in the dark sector, or other, less fashionable options. In the deeper investigation, tensions are not a scandal. They are instruments tuned to find what the simple model might be hiding. Beyond benchmarks and tensions, there are quieter whispers. Large-angle anomalies in the microwave background, hemispherical asymmetries, alignments that seem too tidy, hover at the edge of significance, neither persuasive nor dismissible. The inferred amplitude of lensing in the microwave background appears, in some analyses, slightly higher than predicted by the best-fit model, hinting at either wrinkles in the data or a nudge toward new ingredients. Cross-correlations between cosmic structures and microwave maps search for the fingerprints of evolving potentials and sometimes find them faint, sometimes firm. Each of these hints is treated with suspicion and curiosity in equal measure. The discipline is not to force a narrative, but to keep the measurements clean and the inferences transparent so that any true deviation from the concordance can step forward and be recognized. Amid the data, a conceptual refinement takes place. Distances teach expansion. Shear teaches growth. The two together test gravity itself. If the same dark energy that accelerates the expansion also modifies how structures form by changing the rules of gravity on large scales, then a consistent fit to both distances and growth can betray that change. This is why the deeper investigation is not a list of disconnected measurements but a strategy. It seeks closure relations, ways that independent parts of the cosmic story must agree if the underlying theory is right. Disagreements can point toward new fields that evolve slowly, toward deviations in the ratio of pressure to energy density away from a perfect negative one, or toward modifications of general relativity that become noticeable only across horizons measured in billions of light years. In each case, the data are asked to draw a silhouette of the truth, not write its full portrait at once. All of this, finally, loops back to the central unease. Does the evidence not only show acceleration, but also sketch a future in which isolation deepens until only local islands remain? The candles and rulers do not prophesy, they measure. Yet what they measure when placed together implies that the influence of the smooth component grows with time relative to matter, and that the horizon encroaches. Star formation wanes, communication shrinks, the sky's deep history redshifts beyond utility. No observation can certify that a vacuum decay has begun beyond the horizon, and none can foreclose a late twist in the behavior of dark energy. But the deeper investigation has changed what ignorance looks like. It is no longer the blankness of the unknown. It is a carefully mapped coastline beyond which the sea continues under fog. The instruments have drawn that coastline with care. What waits beyond it? Gentle dusk, sudden rupture, or a surprise that undoes the premise, remains for the next chapters, the next missions, and for the slow, patient ambition to keep listening as the universe speaks ever more softly. Acceleration is not merely a change of pace, it is a change of fate. In a decelerating universe, patience is power. Wait long enough and more of the cosmos comes into view. Light from farther shores eventually arrives. In an accelerating universe, patience is punished. There is a distance beyond which no signal, no particle, no messenger ever crosses. The cosmic event horizon is not a wall one can visit. It is a rule written into geometry. With each passing epoch, additional galaxies slip behind that rule. Their last photons, already en route, will arrive like the final lines of a letter whose author has already vanished from the address book. The observable realm is not shrinking in size, but in influence. The network that once tied clusters and superclusters into a continuous conversation is being cut strand by strand. Within that quiet severing, a subtler transformation takes hold. Gravity has always built islands, galaxies, groups, clusters, bound pockets resisting the general drift. Acceleration promotes those islands from neighborhoods to archipelagos. The local group, with the Milky Way and Andromeda at its core, will merge into a single, larger galaxy bathed in the faint light of long-lived stars. Around it, the ocean of space grows darker and emptier, not because matter disappears, but because it accelerates beyond reach. Cosmology becomes local history. The great filaments that now lace the sky thin into abstractions, their evidence locked beyond the horizon, while the remaining island tends its own fires, then its embers. The choreography of a slow ending can be told as a natural history of energy. Free energy is the ability to do work, to light stars and drive winds and power chemistry against the tide of entropy. In cosmic infancy, gradients abounded, hot against cold, dense against diffuse. Over time, the gradients flatten. Gas collapses into stars. Stars fuse nuclei until the fuel thins, remnants cool and dim, and the light that once heated dust and drove photosynthesis is stretched by expansion until it cannot heat anything at all. The cosmic microwave background, born as a blinding blaze, has already cooled to a near-absolute hush. It will continue to redshift until its wavelengths are so long that they tangle with the plasma within galaxies and can no longer be seen from inside them. Heat death is not a metaphor, it is an accounting. As entropy climbs and usable gradients dwindle, engines stall. The future is not blackness alone, it is equilibrium. Even equilibrium, however, has structure. The stelliferous era, the age in which the majority of light is starlight, has a beginning and an end. It swells, peaks, and declines. In the late chapters, only the smallest red dwarfs remain, sipping fuel with miserly efficiency across time spans that make the age of spiral arms seem like an afternoon. White dwarfs, neutron stars, and black holes become the main repositories of mass. Gravitational encounters, slow but cumulative, eject some remnants into intergalactic space and shepherd others inward. Black holes grow by accretion and by merger. Then, when the infall quiets and the sky empties, they begin the long, soft exhalation of Hawking radiation. The larger the hole, the longer the wait. The radiation is colder than the cosmic background for ages, then warmer when the background cools past it, then finally dominant when nothing else remains to drown it. A universe that once glittered with fusion ends with the faintest hiss of quantum leakage from horizons small and large. In this telling, the ending is patient, orderly, and inevitable. Acceleration complicates this elegy by adding boundaries to memory. With a cosmic event, horizon comes a horizon entropy and a horizon temperature set by the expansion rate. That pairing implies a maximum information capacity for the observable patch, a finite ledger in which the history of states can be written. The implications are as philosophical as they are physical. In a world with finite allowed arrangements, recurrence and fluctuation enter the vocabulary, and the meaning of typical must be handled like a fragile instrument. The universe seems large beyond comprehension, yet the late-time rules hint that what can be known and stored is capped. The mystery deepens not just because distances grow, but because the space of possible stories narrows. Beyond this gentle dusk lie more violent drafts of the ending, conditional on details that observations have not yet nailed. If the smooth energy is not a true constant but a field that evolves, the ratio of its pressure to its energy density can, in principle, slip below -1. In that phantom regime, acceleration becomes superacceleration. Space does not simply expand faster. The rate of expansion itself accelerates in a way that overwhelms all forms of binding. Structures unspool in a sequence. Clusters first, then galaxies, then star systems, then planets, then the atomic lattices of solids, and finally the atoms themselves. The timetable, if such a ratio were confirmed, could be computed from the measured value. It is not confirmed. Current constraints hover near -1 with uncertainties that leave room for calm. Yet the possibility sits on the table like a storm map. Not a promise, but a forecast contingent on a pressure we cannot yet read with sufficient precision. Another, stranger draft begins even earlier, in the vacuum itself. The standard model of particle physics, extended to include gravity as an effective theory, allows a delicate inference from the masses of the Higgs boson and the top quark. Those values place the present vacuum near a boundary between absolute stability and metastability. If the vacuum is only metastable, there exists a lower energy state separated by a barrier. Quantum mechanics permits tunneling through such barriers. A transition, if it occurs, would not rust from the edges. It would begin as a microscopic bubble and expand at nearly light speed. Crossing the wall would be like crossing into a universe with different constants and interactions. Chemistry would fail, nuclei would not be what they were, and the processes that give rise to complexity would be erased. There is no siren for such a front. By definition, no signal can outrun it. This is not melodrama. It is the logical consequence of how fields behave in spacetimes with horizons, and of how energy landscapes can harbor deeper valleys. If such a bubble has already formed beyond the horizon, no observation here can certify it or rule it out. The ending in this scenario could be not just underway, but already decided beyond appeal. Even in the most merciful branch, the one where the smooth energy is truly constant, the vacuum stable, and no superacceleration unfolds, acceleration installs a one-way economics. Distant galaxies speed away. Their light reddens until it fails to energize any process. The inventory of new stars dwindles. The few that remain are dim, red, and long-lived. The supply lines that deliver fresh gas to galaxies are cut by geometry rather than by policy. Civilizations, if they arise in that distant future, will find themselves in closed thermodynamic islands with dwindling reserves of free energy. The cosmic microwave background will be undetectable locally. The Hubble expansion will be invisible because there will be nothing left beyond the bound domain to trace it. In such a sky, cosmology itself becomes harder. The evidence for a hot beginning, an expanding stage, and a late acceleration will be hidden by the very process it describes. The universe writes the proof of its origins on pages that future readers cannot access. This is the deepest twist of the escalation. The more acceleration proceeds, the less the cosmos reveals about its own past to its future inhabitants. Present-day anomalies amplify the sense of unfinished business. The modest tension between the amplitude of matter clustering inferred from weak lensing and the amount predicted by early universe maps could be a laboratory for new physics. A subtle interaction in the dark sector that damps growth, a gently evolving equation of state, or a hint that gravity's rules change by a hair on the largest scales. The continuing discrepancy between local measurements of the current expansion rate and the value inferred from the early universe invites similar speculation. None of these discrepancies yet demand a new theory. Each could fade with improved calibration. But the very existence of robust, competing measurements that point in slightly different directions adds irresolution to the late-time picture. It leaves room for futures that are not exact de sitter, for endings that are not a single script. There is also the question of horizons and information that reaches beyond calculation. Black holes, evaporating slowly in the far future, raise an old paradox in a new setting. What happens to information that falls behind horizons if horizons later disappear? Quantum gravity must answer in a way that respects unitarity while reconciling with the thermodynamics of horizons. The late-time universe is a gallery of horizons. Black hole horizons shrinking, cosmological horizons standing, event horizons setting the stage for what counts as local. If a holographic description of spacetime is correct, if the information content of a region is encoded on its boundary, then a de Sitter future may be described by data on a horizon whose area sets the total number of available states. That picture, still more programmed than settled doctrine, recasts the endgame not as a vanishing, but as an approach to a finite catalog of possibilities. The escalation here is intellectual. The mystery pushes physics toward a theory of quantum spacetime not as an academic luxury, but as a necessity to understand why the end looks the way it does. Amid these drafts of destiny, the question in the foreground gathers weight. If acceleration is real and horizons encroach, then in a precise sense the universe is already in its ending phase. Not the final page, but the final act, the period during which isolation increases, during which the archive of the cosmos becomes harder to read, during which the engines that once wrote structure across the sky quiet their work. The devastating versions, a big rip tearing bonds from galaxies to atoms, a vacuum decay rewriting physics at a light-like front, are possibilities that hang on parameters still being measured. The gentle version, heat death under a constant dark energy, is a baseline as sober as arithmetic. All share a common root, the smooth energy that does not dilute, the rule that when the ratio of pressure to energy density is sufficiently negative, expansion accelerates. This is why the mystery deepens in step with certainty. The evidence for acceleration strengthens as datasets multiply and converge. The consequences of acceleration, explored carefully, reach into horizons, information, and the practical erasure of cosmic memory. The more observers learn about the universe as a whole, the more they discover that knowledge is time-bound, that there is a season in which the cosmos is legible and a season in which it is not. The escalation is not a drum roll toward a single catastrophe. It is a ratcheting of rules that narrow what futures can be and what pasts can be known. In that narrowing, the question from the opening remains, sharpened and unsentimental. If the universe ends not with a single event but with a policy, accelerate, then the ending has already begun. Theory steps in where measurement leaves room. Acceleration has been weighed by candles and rulers, traced in ancient light and present structure, and still it leaves a blank on the ledger labeled what it is. Into that blank enter candidates, some austere, some baroque, each offering a mechanism for a universe whose expansion quickens with time, each carrying consequences for how the ending proceeds. The simplest proposal dresses the vacuum in a constant. In this picture, empty space possesses a uniform energy density that does not dilute as space expands. General relativity reads that smooth energy as a pressure more negative than 1/3 of its density, with the special case of a perfectly constant vacuum registering exactly -1 in the ratio of pressure to energy. Nothing evolves in this sector. It simply persists as the stage grows, and by persisting, it dominates. The future under a true constant is asymptotically de Sitter, a spacetime with a fixed horizon temperature equal to h bar times the Hubble expansion rate h divided by 2 pi kb, and a finite horizon entropy proportional to the area enclosing the observable patch. This version has economy on its side. It fits the data with few parameters and yields a calm, gradual approach to heat death. Yet simplicity is not innocence. Quantum field theory, when asked to compute the energy of the vacuum, returns a value so much larger than observed that the mismatch becomes an indictment. Why should a number be so small and yet non-zero? Why should its influence rise to dominance precisely now? The constant vacuum explains the acceleration, but leaves the origin of its scale as a riddle, and theories that rely on unexplained numbers invite deeper stories. One such story reimagines the vacuum as a field that rolls. In models gathered under the name quintessence, a scalar field moves slowly down a shallow potential, its energy density and effective pressure changing with time. When the field's kinetic energy is small compared to its potential energy, the ratio of pressure to density becomes negative and can approach -1 without equaling it. Such fields can track the dominant component of the universe in earlier epochs, then peel away to dominate late, offering a narrative for the coincidence problem. Acceleration turns on when the field's slow roll allows it. Potentials are chosen to be flat enough that the evolution is lethargic, consistent with observations that find the ratio close to -1 today. The consequences for destiny are gentle but not identical to a pure constant. If the ratio creeps upward toward less negative values, acceleration can weaken in the far future. If it creeps downward, it can strengthen. Even the direction of approach matters. A field drifting toward a minimum might settle, locking the universe into a de Sitter-like fate. A field sliding past a ridge could hasten the dusk. Theories of quintessence also invite interactions, both with matter and within a dark sector, that could change how structures grow. Screening mechanisms may be required to keep such interactions from ruining precision tests of gravity in laboratories and within the solar system. The field is a canvas. Data must paint it with restraint. A more dramatic script pushes the ratio of pressure to density below -1 into the territory called phantom energy. In that regime, the expansion becomes superaccelerated, and the scale factor grows so quickly that a finite proper time in the future sees the divergence of distances. The timeline of disassembly unfolds as a sequence. Cluster potentials fail to bind, galaxies fly apart, star systems unbind, planets lose orbits, molecular bonds stretch and break, and finally atoms themselves are torn. The countdown depends on the measured ratio. If observations were to pin that ratio safely above -1, the specter would recede. Current data allow values near -1 with small uncertainties, leaving phantom scenarios as possibilities rather than predictions. Even as possibilities, they color the map of endings with a brutal chiaroscuro, not a slow ash, but a tearing daylight that overpowers every tether. Some theorists look not to new ingredients, but to new rules. Perhaps general relativity needs revision on cosmic scales. In modified gravity, the same observations of distances and growth are used to ask whether the relation between geometry and stress, energy changes at large distances or low curvatures. Frameworks include theories where the gravitational action is a function of curvature beyond the linear form of Einstein's, theories where gravity leaks into extra dimensions at vast scales, and theories that endow the graviton with a small mass, altering the force law subtly across cosmological horizons. These models often mimic a dark energy-like acceleration in their background expansion, while changing the way structures form. The test, then, is coherence. Distances and growth must fit the same parameters if gravity is unmodified. If they do not, a departure from Einstein's theory may be indicted. The allure of modified gravity is conceptual cleanliness. Perhaps there is no dark energy, only a different grammar for curvature. Its hazard is complexity. It must pass the fierce gauntlet of solar system tests and gravitational wave observations while delivering a measurable change only on the largest scales. Theories that thread this needle exist. The data will do the knitting. There is also a story that begins at the very earliest moment and runs outward. Inflation not only explains flatness and uniformity, in many variants it never ends everywhere. Patches stop inflating and become galaxies and clusters. Other patches continue. The result is a multiverse, a mosaic of regions with different vacuum energies and perhaps different low-energy physics. In such a picture, the smallness of the observed vacuum energy can be framed as a selection effect. Observers arise preferentially in regions where galaxy formation is possible, which requires a vacuum energy not too large. This anthropic reasoning is not a proof. It is an accounting of likelihoods across a vast space of possibilities. Critics object that it risks surrendering predictive power. Advocates reply that it is a reasonable inference when parameters vary across an eternally inflating landscape. For the narrative of endings, A landscape means that different regions meet different fates. Some coast toward de Sitter quiet, some rip, some crunch, some undergo vacuum transitions. The local sky reveals only one tile. The theory proposes the full mosaic. Vacuum metastability anchors another line of speculation with the weight of measured masses. The Higgs field, whose non-zero value endows elementary particles with mass, is described by a potential energy curve with structure. Given the measured Higgs boson mass and the measured top quark mass, extrapolation suggests that the current vacuum may be long-lived but not absolutely stable. If so, there exists a deeper valley separated by a barrier. Quantum mechanics permits tunneling through the barrier, initiating a bubble of truer vacuum that expands at nearly the speed of light. The consequences would be catastrophic for structure and chemistry. The probability per unit volume per unit time of such a transition is tiny by all known estimates, implying survival for times vastly longer than the age already elapsed. Yet acceleration and horizons change the framing. If a transition occurs beyond the event horizon, no advance warning can arrive. The question, is the universe already ending? Gains a literal reading in which a front may be advancing in silence across regions forever causally disconnected. Here, speculation is not an indulgence but a boundary case of known physics applied to unknown domains. Information theory and quantum gravity add another speculative strand. The association of entropy with horizons suggests a principle. The physics within a region may be encoded on its boundary, a holographic description of spacetime. Black holes are thermodynamic objects. De Sitter horizons appear to be as well. If the late-time universe is effectively de Sitter, with a fixed horizon area, then the total number of independent quantum states accessible within the horizon is finite. This finitude underwrites the idea that probabilities and typicality must be handled with care in a world that does not admit unlimited complexity. It also suggests that the endgame is not an abyss, but an approach to a maximum entropy state encoded on a horizon. To reconcile this with quantum unitary evolution, and with the apparent evaporation of black holes by Hawking radiation, requires a theory of quantum spacetime that is still under construction. Ideas from string theory, loop approaches, and newer holographic dualities offer sketches. Their common theme is that horizons are not mere absences. They are thermodynamic actors whose bookkeeping governs what endings are allowed. A different class of speculations addresses tensions in the data. If the local expansion rate truly exceeds the rate inferred from early universe parameters, then something about the late-time energy budget or the early-time sound horizon may differ from the simplest model. Early dark energy, an episode in which a small fraction of the energy density behaves briefly like a cosmological constant around the time of photon decoupling, can shrink the sound horizon and elevate the inferred local expansion rate without changing late-time behavior drastically. Interacting dark sectors, in which dark matter slowly exchanges energy or momentum with a dark energy-like field, can adjust the growth of structure and ease discrepancies in lensing amplitudes. None of these proposals is yet demanded. Each is constrained by a web of observations, but they illustrate a virtue of speculation disciplined by data, to map the shape of permitted departures and thereby learn what kinds of endings remain on the table. Even the simplest constant vacuum invites speculative context. Perhaps the number is small because of cancellations between contributions from known fields and unknown ones, a delicate balance enforced by a symmetry broken at absurdly low scales. Perhaps the value cannot be calculated from within a single vacuum, and instead is selected in a multiverse by counting observers. Perhaps what is called a constant is an emergent, coarse-grained description of horizon thermodynamics, and its value reflects the bookkeeping of information rather than a fundamental parameter. These are not mutually exclusive. They are overlapping attempts to translate a stubborn fact into a physical sentence that does not offend proportion. Destiny follows these choices. A true constant writes a slow elegy. Horizons fixed, heat death approached, black holes evaporating in an almost silent finale. A rolling field can alter the tempo, gently relaxing acceleration or, if driven, hastening it toward phantom extremes. Modified gravity can bring surprises in the relation between distance and growth, changing the architecture of the last structures to form. Vacuum metastability replaces elegy with rupture, not scheduled but possible in principle at any time and beyond all alarm. Holographic endings replace the metaphysics of infinity with a finite library of states approached asymptotically. In each case, the question of whether the ending has already begun becomes precise. Under a constant, it has. Isolation increases, information caps, entropy climbs. Under a rolling field, it likely has as well, though with the caveat that a late reversal is not forbidden. Under phantom, the ending is a countdown. Under metastability, the ending may already be underway beyond the horizon, indifferent to knowledge. Under modified gravity, even the definition of an ending may shift with the rules. Speculation is not a license to invent. It is a scaffolding around a building already sketched by data. The accelerating universe has narrowed the space of plausible ideas to those that either supply a smooth, negative pressure component or alter gravity, so that geometry and matter conspire to mimic one. Within that space, each proposal is a wager about what the vacuum is, how fields live on spacetime, and whether horizons are thermodynamic or merely geometric. The fate of everything flows from those wagers. Until instruments pry more facts from faint light and weak shear, theory will carry the burden of imagining the engine of acceleration, and with it, the manner of the end. The mystery has a laboratory the size of the sky. Its instruments are not singular machines, but a choreography of mirrors, cryostats, fiber feeds, microwave horns, and interferometers tuned to the faintest murmurs a universe can make. Acceleration is the headline, but the daily work is calibration, tying distances to anchors, shapes to truth, spectra to time, and every uncertainty to a ledger that can survive scrutiny. In this chapter, the tools step forward, not as props but as characters, each carrying a question it is born to ask. The distance ladder, once a fragile scaffold, has become an engineered bridge. At its base stand geometric anchors, water megamacers orbiting supermassive black holes in tight, almost Keplerian disks, their radio emission tracing precise velocities and radii. From such orbits, a true distance is carved without reliance on standard candles. Nearby, the tip of the red giant branch provides another rung. Stars at the moment of helium ignition reach a near-universal luminosity in certain bands, allowing the edges of old stellar populations to serve as yardsticks. Gaia's astrometry pins positions and motions with micro-arcsecond care, turning parallax from a 19th century dream into a census of distances within the Milky Way. With these anchors, Cepheid variables are calibrated. With Cepheids, Type 1a supernovae are calibrated. With supernovae, the Hubble flow is traced across hundreds of megaparsecs. Each step is a handoff between communities of light. Time delay cosmography adds a second ladder running in parallel, one that uses the universe's own lenses. When a foreground galaxy bends the light of a background quasar into multiple images, variability in the quasar's flicker arrives along paths of different length and gravitational potential. The arrival time delays, combined with exquisitely modeled mass distributions in the lens, reveal absolute distances that do not depend on stellar standardization. High-resolution imaging from space and from adaptive optics on large ground-based telescopes resolves lensed host galaxies into rings and arcs, sharpening the mass models. In the background, stellar kinematics in the lens galaxy break degeneracies in how mass is distributed. The delays are measured over years. The geometry is carved from light. The result is a value for the cosmic expansion rate today, h0, whose independence from the traditional ladder renders it a crucial crosscheck and a negotiator in the current tension between early and late measures. Standard sirens extend the triangulation into a new messenger. Gravitational waves from merging compact objects carry an amplitude that falls in a known way with distance, thus providing an absolute luminosity distance without any intermediate calibrators. When an electromagnetic counterpart identifies the host galaxy, the redshift of that host completes the distance, redshift pair. The first such event already demonstrated the principle. Dozens more, spread across the sky and out in redshift, will change principle into precision. Even without light, a statistical association between events and large-scale structure can recover redshifts. Black hole binaries contribute in a different mode. Their distribution and any subtle environmental signatures can add population-level constraints. The aim is clear. With enough sirens, the expansion history and perhaps even the time variation of the smooth component's pressure, density ratio, can be mapped by a messenger indifferent to dust and calibration drifts. If distance is one pillar, growth is the other. Weak gravitational lensing surveys transform the sky into a field of sheared ellipses, each galaxy's shape nudged by the integrated gravity of everything between source and observer. Wide-field imagers now tile thousands of square degrees with repeated exposures, building depth and redundancy. Point spread functions, the fingerprints of optics and atmosphere, are modeled star by star and frame by frame. Algorithms known as metacalibration and image simulations iterate toward unbiased shear. Photometric redshifts, derived from multiband colors, place galaxies into tomographic slices so that growth can be measured as a function of time. The shot is delicate. Millipercent biases in shape or redshift propagate into percent-level biases in the amplitude of matter clustering. The payoff is profound. Lensing sees both dark and luminous matter. It is gravity's census rather than light's. When lensing's picture of growth is compared with the expansion history inferred from distance measures, gravity's consistency across scales is tested. Any persistent mismatch can point to a dark energy that interacts or to a gravity that deviates gently from Einstein's at horizon distances. Redshift surveys work in lockstep with lensing. Fiber-fed spectrographs bundle the light of thousands of galaxies at once, prying from it the precise stretching that reveals motion with respect to the expanding stage. From these maps emerges the baryon acoustic ruler, the preferred scale seeded by sound in the early plasma, imprinted in the present-day clustering of galaxies. Measuring this feature at many redshifts yields a ladder of distances and expansion rates that is tied to early universe physics by the microwave background. Beyond the ruler, redshift space distortions, squashings and stretchings of clustering along the line of sight caused by coherent infall and outflow, trace how eagerly structure collapses. The combination is a lever. Distances and growth handled together can discriminate between a smooth dark energy fluid and a modification to the relation between curvature and stress, energy. The microwave background, though ancient, continues to speak in new dialects. Polarization maps, far subtler than temperature maps, isolate modes generated by scattering at recombination and by gravitational lensing along the line of sight. Reconstructing the lensing deflection field sharpens constraints on the amplitude of structure and on the sum of neutrino masses, the latter a parameter that damps growth and thus entangles with dark energy in subtle ways. Improved measurements of large-angle polarization pin down the optical depth to reionization, cleaning early universe parameters that feed every late-time inference. At smaller angular scales, the Sunyaev, Zeldovich effect, hot electrons in galaxy clusters boosting the energy of CMB photons, builds catalogs of clusters whose abundance and evolution constrains growth and geometry together. Cross-correlations between microwave maps and galaxy surveys extract the integrated Sachs-Wolf signature, a direct imprint of evolving gravitational potentials in a universe where smooth energy becomes important. Each of these is a thin thread. Braided, they hold. A newer frontier listens not to starlight but to hydrogen, whisper, 21 centimeter intensity mapping measures the aggregate emission of neutral hydrogen without resolving individual galaxies, painting low-resolution, enormous volume maps of structure. The method is fast, statistically mighty and hard. Foregrounds from our own galaxy and from extragalactic radio sources are many orders of magnitude brighter than the cosmic signal. Instrumental systematics, beam chromaticity, calibration stability must be conquered. Pathfinders have learned this vocabulary. Future arrays will apply it to detect the baryon acoustic feature with radio waves, to measure growth on large scales, and to reach into redshift ranges where optical surveys thin. Paired with optical lensing, the technique unlocks multi-tracer strategies that beat down cosmic variance, the fundamental limit set by having only one universe to observe. A different long patience belongs to redshift drift. The concept is severe. Take the spectrum of a distant quasar today, and again decades hence, and measure the minute change in the redshift of narrow absorption features written by intergalactic hydrogen. The sign and magnitude of this drift depend directly on whether expansion is slowing or speeding up at the observed epoch. The experiment requires spectrographs with stability beyond the already heroic, and a community capable of sustaining a baseline longer than the careers that begin it. Its virtue is purity. It reads the expansion's acceleration as a clock reads time, without ladders, calibrators, or cross-correlations. Instruments on extremely large telescopes with diameters measured in tens of meters are designed with this in mind. Their calibration systems tied to laser frequency combs, and their optics enshrined in temperature-controlled vaults. No instrument works alone. The era of single-survey cosmology is over. The science is born in combinations. Supernova light curves rely on host galaxy stellar populations mapped by imaging surveys. Lensing shear catalogs depend on photometric redshift, refined by spectroscopic subsets. Baryon acoustic distances are interpreted with priors from the microwave background. Gravitational wave sirens are localized by wide-field optical and radio facilities that can find kilonovae within hours. Cross-correlation is both method and ethic. Map A is multiplied by map B, and the product yields a term that neither map carries alone. With cross-correlation comes immunity to some systematics, because independent instruments rarely share the same flaws. With it also comes a new vulnerability: the need for consistent sky coverage, calibration standards, and data sharing across consortia whose cultures and pipelines differ. To meet this, modern cosmology has adopted blinding. Analysis choices are frozen and key numbers are hidden until every systematic test passes, to guard against the invisible pressure to prefer results that soothe tensions. Simulations sit behind the observations like rehearsal spaces behind performance halls. Dark matter only runs with trillions of particles chart the growth of the cosmic web. Hydrodynamic simulations layer in gas, feedback from stars and black holes, and radiative transfer to model how galaxies and clusters light up gravity scaffolding. Fast emulators, trained on suites of simulations, predict observables across parameter space without requiring a fresh run for every setting. Synthetic skis, mock catalogs that imitate survey footprints, noise, and selection effects, allow pipelines to be tested end-to-end. If a lensing survey claims a bias below 1%, it must demonstrate that claim against skis where the truth is known. If a redshift survey extracts a ruler scale, it must show that fibers, weather, and tiling do not nudge the answer. The fidelity of simulation is itself a research program. Its reward is the ability to translate raw counts and shapes into statements about the pressure and fate of the vacuum. On the horizon, new observatories promise not single leaps but long strides. Space telescopes tuned to infrared wavelengths will conduct high-latitude surveys that measure billions of galaxy shapes for weak lensing and collect spectra for precise baryon acoustic distances. A European mission devoted to dark energy has already opened its eye, mapping shapes and spectra with a precision designed to reduce statistical errors to the point where systematics must be the center of attention. A wide-field survey from a mountain in Chile will scan the sky nightly, discovering supernovae by the tens of thousands, monitoring time delay lenses, and building a lensing catalog of unparalleled depth and area. Microwave experiments with hundreds of thousands of detectors cooled to a fraction of a degree above absolute zero will map polarization and lensing over large sky fractions, constraining neutrino masses and the arcane details of recombination that echo into every other dataset. Radio arrays will lengthen baselines and quiet their electronics, turning 21-centimeter intensity mapping into a routine instrument rather than an experiment of proof. Not every tool measures the cosmos directly. Some prod the foundations. Particle colliders measure the properties of the Higgs boson and the top quark with growing precision, tightening inferences about whether the present vacuum is stable or only metastable. Neutrino experiments weigh the flavor hierarchy and the absolute mass scale, parameters that dark energy surveys feel through their effect on growth. Searches for ultralight fields, axion-like candidates whose wave-like nature alters structure on small scales, intersect with cosmology's lensing and clustering statistics. Even tabletop experiments that test the inverse square law of gravity at millimeter scales remind theory that any proposed modification must pass in laboratories before it earns a place in the sky. The work is as much cultural as technical. Data releases must be complete and documented. Covariance matrices must be shared. Null tests must be published even when they show the expected nothing. Reproducibility becomes a moral stance. Pipelines open-sourced, random seeds logged, version control written into papers. The field has learned that the most dangerous systematic is the one unimagined. To guard against it, teams cultivate redundancy, overlapping instruments, repeated observations, alternative calibrations. Community challenges, where independent groups analyze the same synthetic data blind, reveal hidden assumptions. The end is not a single number, but a multidimensional surface of constraints on parameters that describe the pressure, clumping, and grammar of gravity on the largest scales. Against this machinery, the central questions are phrased with care. Is the ratio of pressure to energy density for the smooth component exactly -1, or does it evolve? Are distances and growth consistent under general relativity across all scales probed? Or does a hairline crack appear when the sky is used as a laboratory? Is the discrepancy between early and late time measures of the expansion rate a herald of new physics or a lesson in humility about systematics? Do gravitational waves, arriving by the hundreds, settle the argument or complicate it with fresh nuance? Can redshift drift be heard at last, a direct meter of acceleration unmediated by ladders? What the tools seek, collectively, is closure, a model that fits distances, growth, light, and gravity without hidden tensions, or a persistent, statistically hard discrepancy that points unambiguously beyond the simple picture. Either outcome narrows destiny. If the smooth energy is a true constant, the future approaches a de Sitter hush with horizons fixed and entropy mounting. If the pressure, density ratio slides even slightly, the clock of the ending speeds or slows. If gravity itself shifts its grammar at horizon scales, the architecture of the last structures may surprise. The instruments do not prophesy. They measure. But measurement, when it becomes a chorus sung across wavelengths and methods, is prophecy of a kind, the only kind science permits, an ever sharper silhouette of what the universe is doing and how the final act will unfold. The story that has unfolded is not a countdown, but a change in weather. Acceleration does not toll like a bell. It drifts like winter arriving in slow degrees, a season whose first frost has already touched the leaves while the trees still look green from a distance. In such a cosmos, the idea of an ending becomes unfamiliar. It is not a single impact or a last flare. It is a policy written into geometry, expand faster with time. Under that policy, horizons form, communication narrows, free energy thins, and the archive of the universe, its ability to remember itself, grows fainter with every step forward. The question, is the universe already ending, begins to sound less like melodrama and more like a sober description of the present tense. Across that landscape, meaning still appears, brief, bright, localized, like campfires on a dark plain. Life is the art of building islands of order in a rising sea of entropy, borrowing gradients of energy and paying back a slightly larger disorder to the larger world. Stars do this without reflection. Biology does it with reflection, capable of turning awareness onto the sky that feeds it. Civilizations inherit that talent and aim it outward with mirrors and radio horns, with equations learned by heart and then doubted in the next breath. That such cultures arise at all is a ferocious improbability made ordinary by time and number. Their presence does not cancel the policy of acceleration. It occupies a chapter within it. The dusk gathers, and still there is music in the air. Philosophy in this setting is not a set of slogans about insignificance. Scale is not a measure of worth. The largest things are not the most meaningful. They are only the most extended. The human nervous system, kindled for a handful of decades, is the only aperture through which galaxies ever become galaxies, shapes with narrative rather than mere distributions of mass. Knowledge exists nowhere but in minds that host it. In this sense, a species that learns the sky is not a footnote to cosmology. It is the condition under which cosmology becomes a story rather than a list of numbers. The future may silence the long-distance conversation. The present makes the conversation possible in the first place. To recognize a horizon is already to have transcended it in understanding, if not in travel. The horizon itself has the haunting dignity of a coastline seen from a cliff. It marks an end to influence, not an end to being. Beyond it, galaxies continue their histories, stars ignite and age, worlds warm and freeze, perhaps even minds awaken and ask their own versions of these questions. None of that can be reached or heard from here. The recognition can breed a loneliness that is not romantic but structural, a solitude set by the metric of spacetime rather than by temperament. Yet it can also sharpen a different instinct, to care for what remains within reach. When the cosmic conversation tenses into archipelagos, stewardship becomes less a sentiment and more a survival skill. The local group, or whatever island hosts a civilization, becomes a garden with a finite well of free energy and a bounded library of knowable history. In such a garden, responsibility is not grandiose, it is practical. Stars are rationed by nature, knowledge is rationed by time, kindness is rationed only by choice. There is a quiet courage in measuring a universe that tends toward silence. Instruments that count faint photons and map cold ripples do more than fill journals. They enact a kind of defiance, not a denial of fate, but a refusal to let fate define value. The act of learning in a universe with a closing horizon is a secular form of prayer, an attention so complete that the subject and the one who attends are both changed by it. Telescopes and detectors are not merely tools, they are forms of care. They say that reality is worthy of being known while it can be known, and that knowing is a form of belonging. The numbers they deliver, densities, ratios, exponents, sound austere, but stitched together they reveal a biography. A hot beginning, a flowering of structure, an onset of acceleration, a long afternoon of cooling. To tell that biography is to place every local joy and grief on a wider stage, not to diminish them, but to let them be seen for what they are. Bright, temporary patterns under a sky that will not always speak this clearly. The moral anxiety that sometimes shadows cosmology usually arrives wearing two masks. One asks, if everything dissolves, why bother? The other asks, if endings may strike without warning, if a vacuum can slip to a lower state beyond all alarm, how to live without dread. Both masks mistake knowledge for prophecy. The first forgets that value is made locally by beings with limited time. Nothing about a far heat death forbids a near tenderness. The second forgets that uncertainty is not an enemy but the ground on which attention grows. The possibility of vacuum decay does not command fear, it teaches proportion. Even in the most alarming scenario, there is no strategy beyond living well in the hours given. Cosmology does not subtract a single kindness, a single work of craft, a single gesture of justice from the ledger of what matters. It only adds context, vast cooling context, within which those acts stand out with sharper relief. Consider, too, the justice owed to future minds. Acceleration ensures that later observers, if any exist within bound islands, will inherit a sky that hides its own birth certificate. The cosmic microwave background will slip beyond the technical possibility of detection. Distant galaxies will depart the census forever. The Hubble flow will be unreadable in local motions. The great clues that made the story legible today will be gone. The present, then, is a hinge era, the window in which evidence reaches across time and tells a coherent tale. To live in such an era is to be drafted into a duty that is almost archival, preserving knowledge of the initial blaze, of the eras of structure, of the onset of acceleration, becomes a gift to those who will not be able to reacquire it from scratch. In this light, a data archive is not a server rack, it is a time capsule. A textbook is not a curriculum, it is a message to a future where the sky lies about its past. To tend such messages is an ethics made of patience. If destiny is a set of branches, calm heat death under a constant vacuum, a gentle modulation under a rolling field, a tearing in a phantom future, a sudden rewrite under metastability, then humility is the only fitting posture before them. None of these endings consults preference. Each is an inference that flows from equations and measurements, tuned by error bars and tested by instruments that can fail or deceive. The willingness to revise, to hold conclusions as conditional, and yet to act decisively on what is best supported today, is not an academic habit, it is a survival trait. A species capable of building detectors can also build stories that do not congeal too early into dogma. That ability will matter as the data complicate, and as tensions between measurements either dissolve into clarity or harden into evidence for new physics. The end of everything is not a theme to be owned. It is a horizon against which thought must learn to sail. Even the image of heat death, so often painted as a gray vacancy, contains an austere beauty when viewed properly. Equilibrium is not a void. It is a final balance where gradients no longer provoke change. Before that balance, black holes evaporate in glacial whispers, horizons tend their thermodynamic ledgers, and the last red dwarfs consume their fuel like monks extending a candle's life by pinching the wick. There is pathos there, but also elegance. A universe that writes the conditions for life, then for mind, then for knowledge, and finally for quiet is not tragic by design. It is complete by process. The completeness does not console, it clarifies. It suggests that meaning, if it is to be found, is not a property of the whole future but of the lived present within it. In this frame, the extraordinary flowering of cosmology over a few human generations becomes more than a scientific success. It becomes a cultural event on the scale of species biography. A creature that learned to walk upright also learned that space-time bends, that galaxies recede, that an afterglow from the beginning rains down in microwaves, that a smooth energy now steers the largest motions, and that horizons both conceal and instruct. The achievements do not erase suffering or resolve injustice. They place them alongside a cathedral of understanding built from careful doubt and quiet discipline. To stand beneath that cathedral is to feel both small and necessary. Small, because the building is larger than any life. Necessary, because without minds to notice, the building is mere stone. The end, then, is neither a threat nor a comfort. It is a backdrop. Within it, conversations continue. Children learn constellations that belong to their epoch, and laboratories hum. Within it, decisions are made about how to share a planet's finite warmth, how to govern a civilization's appetites, how to distribute the work of attention so that the sky is not abandoned to noise. Within it, poetry and physics sit at the same table and trade metaphors honestly. Horizons in equations, horizons in the heart. Both know that the universe is already ending in the precise sense described by acceleration and entropy. Both also know that endings, properly understood, do not cancel beginnings, they frame them. At the close of this long inquiry, the mystery remains intact. That is its virtue. If a constant vacuum rules, the horizon is fixed and the library of states is finite. If a field rolls, the tempo shifts. If spacetime's grammar changes, the last structures will surprise. If a deeper vacuum waits, the stage can be reset without appeal. Each path is impersonal and vast. Against that vastness stands the local, hands on an eyepiece, code on a screen, a quiet intake of breath when a spectrum reveals a line from a galaxy whose light began when continents were young. These are not footnotes to fate. They are the whole of value as far as any mind can know it. So the narration settles into a tone proper to a long twilight. Not alarm, not resignation, but attention. The universe is already ending in the way that matters to horizons and archives. Within that ending, light still arrives, instruments still listen, and meaning is still forged between evidence and wonder. The final act is not a curtain drop, it is a deepening blue. In that blue, a species can choose to be faithful, to each other, to the work of understanding, to the fragile, temporary gift of a sky that still tells its story to anyone patient enough to hear.